Welcome back, Mr. Klinkerman again. We are continuing our lesson in section 7.6 in which we're trying to learn ways in which the derivative can help you with a graph of a function. And we're into the third learning goal, although truly there's a couple other things in this section. This is a long section. A couple other things in this section we'll have to learn. But we've already looked at how you use the first derivative to determine when a function is increasing or decreasing, how you use the first derivative to determine where the relative extrema of a function are located, and now what we're going to do is we're going to use the second derivative. And we're going to use the second derivative to do a couple things, to find what are called inflection points and to determine the concavity of the function of a graph on specific intervals of the graph. Alright, let's get into that. I have here for you a function. Its first derivative and second derivative already figured out. You can do the math to see how you get those two derivatives from the original, but it's pretty simple. What I want to focus on mostly is the graph of the function and how it relates to the second derivative of the function. So we're going to do a whole lot in this example with looking at how f double prime of x compares with the graph. Well, before we get to that, what we've learned about the first derivative so far is this, that the first derivative tells you when a function is increasing or decreasing, and it helps you find out where the relative extrema are. Alright, so for instance, this graph is increasing on that interval and this interval right there. And then it's decreasing between those two on this interval. And we said that you could, that's one of the things the first derivative tells you. So it's positive on those two purple intervals. The first derivative is negative on that light blue interval. And it would be equal to 0 at these relative extrema. You've got a relative max and a relative min. Okay, that's all the things that you can determine using the first derivative. With the second derivative, we're not trying to worry about increasing and decreasing intervals. You can worry about relative extrema with this, but that's not the point of this video. We first want to talk about the concavity and how the second derivative relates to the concavity of a graph. And what concavity means is simply is a graph kind of opening downward like this. That's an example of concave down. Or is the graph opening upward like this on an interval, which you would call concave up. And then in addition to determining where the graph is concave up and concave down, the other thing that we're going to do is we're going to try to find the points where the concavity changes, which you can see is that point right there on this graph. And what that point is called is simply a point of inflection. Now let me label some things here. Alright, you see the portion of the graph that's concave down, the portion of the graph that's concave up, and the point of inflection. Alright, now I told you we're trying to relate those things to the second derivative, and quite simply, here's how that's going to work. When you're trying to figure out where the graph is concave up or concave down, what you're going to try to do is figure out where is the second derivative positive and the second derivative negative. And real easily, when the second derivative is negative, you're going to have a concave down portion of your graph. And when the second derivative is positive, that portion of the graph is going to be concave up. And then it turns out the place where the point of inflection happens, where the graph changes from concave down to concave up, is going to be the place where the first derivative, sorry, I keep saying first derivative, it's going to be the point where the second derivative is equal to 0. Alright, so I'm going to put some rules on your screen right now that basically sum up what I just said. Alright, if the second derivative is greater than 0, for all x's in an interval from a to b, then function f is concave up on that interval from a to b. So when the second derivative is positive, the graph is concave up. If f double prime of x is less than 0, in other words, if the second derivative is negative for all x's in the interval a to b, then f is concave down on that interval from a to b. And then finally, a point on the graph of f is an inflection point if the second derivative equals 0 and the second derivative changes sign at that point. Now, we haven't talked about that yet, but the concavity just does have to change from positive to negative or vice versa at a particular point in order for there to be a point of inflection. The concavity has to change for there to be a point of inflection. All right, well, let's look at how those things relate to this graph. Now, you can do the math on your own, but I think it's pretty simple math here as well. Okay, first thing I want to point out to you is that the point where the second derivative is equal to 0 is when x is equal to 1. And of course, the way you find that is simply you set the second derivative equal to 0. And you can see that the second derivative is equal to 0 when x is equal to 1. All right, and so what that tells me is that at the point when x equals 1, now if I plug in 1 into the original function f of x, I get 1 minus 3 minus 4, so negative 2, I get negative 6. At the point 1, negative 6, all right, which you can see is about right there on the graph, I have a point of inflection. All right, so there's an inflection at 1, negative 6. So second derivative equals 0 shows you where a point of inflection can exist. Now, I've kind of ignored the second part of that so far, where the concavity has to change from positive to negative or vice versa, but I'm getting to that. All right. Second thing you want to notice is that the second derivative is negative on that interval from negative infinity to 1. Okay, and look at that interval. From negative infinity to 1 is this portion of the graph that goes all the way from the far left to our point of inflection. Second derivative is negative for anything on that interval. Pick a value. Let's say find f double prime is 0. All right, well, f double prime of 0 would be negative 6. So second derivative is negative, and any value of x along that interval will have a negative second derivative. Therefore, the graph is concave down there. Finally, the second derivative is positive on the interval from 1 to infinity. So if we start at that inflection point and we consider the entire rest of the graph, the first derivative is positive, and therefore the graph is concave up on that interval. I keep saying first derivative, you know I mean second derivative in this case. The second derivative is positive, so the graph is concave up over that interval. All right, and it's real easy to demonstrate that that's true. If you just pick any value of x along that interval, say f double prime of 2, and evaluate in the second derivative, you get 12 minus 6. You're going to get a positive value for the second derivative. Okay, there you go. So, second derivative equals 0 can find you a point of inflection. When the second derivative is positive, shows you where a graph is concave up. And where the second derivative is negative, shows you where the graph of a function is concave down. Let's try some examples. What we're going to look at in this example is how you use the second derivative to find the intervals where a function is concave up and concave down. We'll also talk about the point of inflections, despite the fact that I did not include that in the directions here. Okay, now for time's sake, I'm going to go ahead and show you what the first derivative and the second derivative of the function are. You ought to pause the video and try to find them on your own so that you know that you can do that math. On a test, I'll expect you to be able to do that math. All right, but we are going to be using the second derivative here, and so we're going to take the derivative of f of x, and turns out that f prime of x for this function is going to equal negative 2x over x squared plus 4 squared. All right, that's just a simple application of the quotient rule right there, or product rule if you choose to rewrite the original expression. And then the second derivative, in which you have to use the quotient rule and the chain rule whenever you're finding the derivative of the lower function, second derivative ends up being this. F double prime of x is 6x squared minus 8 over x squared plus 4 cubed. Okay, now in order to determine where the function is concave up and concave down, we have to find the places where the graph could possibly change concavity. Either the points of inflection or vertical asymptotes, as it turns out. Alright, so for instance, here's a little curve where the concavity changes from concave up to concave down. Alright, we would want to find out where that occurs, or maybe it's something where the graph changes from concave down to concave up. We need to know where a point of inflection would be in order to find those two things. Or, of course, anytime you have a vertical asymptote, the graph on one side of the function could have a different concavity than the graph on the other side of the function, or it could have the same concavity as the graph on the other side of the function. Alright, but at any rate, the concavity can change at vertical asymptotes, and so those are important whenever you're trying to figure out where the graph is concave up and concave down. Okay, enough of the background information. What we need to do is we need to set the second derivative equal to 0, and we're going to use that to try to find the places where the concavity can change. Alright, so we're going to set 6x squared minus 8 equal to 0. Truly, we don't have to worry about the denominator, because if we set the denominator, or the whole fraction equal to 0, and we multiply both sides by the denominator, it's going to go away. Alright, and when 6x squared minus 8 is equal to 0, you get x is equal to plus or minus 2 over the square root of 3. I'll let you do the math to get there. And that is approximately plus or minus 1.15, and I'll put it that way just because it's going to make the explanation for this next part a little bit easier. Okay, now that we know where the possible points of inflection are, the places where the concavity can change, what we're going to do is similar to what we did with the first derivative prior to now. We're going to look at the signs of the second derivative at different intervals on the graph. And the way we're going to choose those intervals is we're just going to pick those 2 points where the second derivative is equal to 0. Negative 1.15. Ooh, that's not the marker I wanted to use. Or positive 1.15. And we're simply going to see when is the second derivative positive and negative on the intervals between and around those two values. And you see on the screen up in the top right now those intervals that I'm discussing, from negative infinity to negative 1.15 and so forth. What we would like to do is simply pick some values on those intervals. Let's say from the first interval we pick negative 2, and we want to find out what is the sign of the second derivative of negative 2. Okay, now I'll let you again do the math. But it turns out that when the second derivative is negative 2, that the second derivative is positive. So, there we go. That's the sign of the second derivative over that interval. And then between negative 1.15 and 1.15, it makes sense to use 0. And whenever you figure out what f double prime of 0 is, you're going to find that it's negative. And then you could use positive 2 and plug that into the second derivative to find out on that last interval what the sign of the second derivative is, and you're going to find out that it's positive right there as well. Okay, so we had two possible points of inflection, places where the concavity could change. And the concavity, remember, is dependent upon the sign of the second derivative. Now, here, as you get to negative 1.15, we had something that was concave up, and then it switched to concave down. So there was a point of inflection. And that point of inflection is when x equals negative 1.15. Then, when we approached positive 1.15, we had a concave down to the left side of the interval, and then it switches to concave up on the right side of the interval. So there is another point of inflection at positive 1.15. Okay, now how do we answer this question directly? It said to note where the intervals of the function are concave up and concave down. Well, let's do that. All right, quite simply, let's just label our answers here. We're going to say, where is the function concave up? Well, it was concave up on the interval from negative infinity to negative 1.15, if I'm using three significant figures instead of an exact value. And it was concave up on the interval from 1.15 to positive infinity. Those are the two intervals where the second derivative was positive. And then the function was concave down, where the second derivative was negative, and that was from negative 1.15 to positive 1.15. And even though I didn't ask it, we can say that there's a point of inflection at two places, actually. One of those is at negative 1.15, comma, 0.188. Now I got the y coordinate for the point of inflection from the original function itself. Okay? And then the other point of inflection is at positive 1.15 and still 0.188. There you go. That's how you find concavity and points of inflection. Now that's as much as the videos you're required to watch. I do have one more example for you that you can try and kind of see how the work goes. I'll tell you what, I do want you to see the graph of this function just to make sure that it's right, but then you don't need to see the next example. So take a look at this. And you can see indeed that from negative infinity to the negative 2 divided by the square root of 3, that was a negative 1.15. The graph was concave up. And then once again, after positive 1.15, 2 divided by the square root of 3, the graph was concave up. And then between those 2 points of inflection, the graph was concave down. Alright, so great job. Let's try one more if you want to watch another one. Okay, and if you're watching this, what I would like you to do is go ahead and pause, find the first and second derivative, set the second derivative equal to 0 to try to find the places where you can have a concavity change, the possible points of inflection, and then try to see on what intervals the second derivative is positive and negative. Okay, now pause it, try that. I'll be working it while you do so. Great, so you should have found that the first derivative is x minus 4 squared times 4x minus 4. And the second derivative is x minus 4. Promise that's a 4, times 12x minus 24. Now, if you didn't get those exactly, either you made a mistake with your differentiation, or you just didn't use some nice factoring that would make these expressions look a little bit simpler as you see them right here. Okay, and now you know the next thing to do is to set the second derivative equal to 0. And when you set the second derivative equal to 0, you're going to see that the possible points of inflection are x equals 4 and x equals 2. And so what our job is now is to find out what the sign of the second derivative is surrounding those points. Okay, now a little bit of work there. It turns out that the second derivative of 0 is equal to 96. And I chose 0 because it's in that interval from negative infinity to 2. So that means that the second derivative is positive until you get to 2. Then the second derivative of 3, so a number between 2 and 4, is equal to negative 12. So the second derivative is negative on that interval. And second derivative when x is equal to 5 is positive 36, telling you that after 4, the second derivative is going to be positive the entire way. And so based on that, we can see that this graph is going to be concave up on the interval from negative infinity to 2, as well as the interval from 4 to infinity. The graph is concave down on the interval from 2 to 4. And because when x equals 2 and x equals 4, the concavity changed, that means that we had inflections at the points where x is equal to 2 and where x is equal to 4. And you can simply find out what f of 2 and f of 4 are in order to determine what those exact points are. And you'll find that those points are 2, negative 16, as well as 4, 0. Alright, appreciate your attention to this. It's not difficult, it's just tedious, that's all. But it's a very useful tool in analyzing the graph of a function. That's how I use the second derivative. I'll see you next time.